Central Limit Theorem is now going to connect what we know about sampling distributions, their means and their standard deviations, to how we can calculate probabilities of specific sample results occurring. The important part of the central limit theorem is that one of these two situations must be true for you to use the related properties. So if we take random samples of size n has to be at least as big as 30. So in our previous example, we worked with a very small sample size. Generally, we avoid small samples. That was just to make the math easier. To use the central limit theorem, you have to have sample sizes bigger than 30. And if you know the population mean and standard deviation, then that sampling distribution of sample means will approximate a normal distribution. The bigger the sample size, the better the approximation will be. So what we're saying is in number one here, if this is what your population distribution actually looks like, and you take and create the sample distribution of sample means with sample sizes bigger than 30, you're going to turn it into a normal distribution. And that's really important because then we can use all the things we just learned about finding probabilities from normal distributions with these sampling distributions. Now, if your sample size isn't that large, then if random samples of size n are drawn from a population and you know the population is normally distributed, then the sampling distribution of the sample means will be normally distributed for any sample size n. So that's what the second picture is explaining, is if you, again, have a sample of any size, but you know it came from a population that was a normal distribution, then the distribution of the sample means is also going to be a normal distribution. And again, we'll be able to use the things that we know about probabilities for normal distributions. To use central limit theorem, you're going to make sure one of these two things is true, and then you're going to be able to use the properties that we just discussed. You can find the mean of the sample means by knowing it's going to be the same as the population mean. The variance we didn't specifically talk about, but this is what its formula would look like. The more important one is the standard deviation of the sample mean, and this is again the formula we were just looking at. So once again, examples are really helpful here to make all of this make some degree of sense. In example 2 in this section, a study analyzed the sleep habits of college students. The study found that the mean sleep time was 6.8 hours with a standard deviation of 1.4 hours. You take random samples of 100 sleep times from this population, and the mean of each sample is determined. So again, I have the entire data set, and I'm going to randomly take samples of 100 of those sleep times. So I take a sample of 100, then I find its mean. I take another sample of 100, and I find its mean. And again, these samples can overlap. They can include some of the same pieces of data. So part A asks us to find the mean and standard deviation of the sampling distribution of sample means. To create that sampling distribution of all the possibilities of samples of size 100 would be very difficult, but we can use the central limit theorem here if it applies. So first of all, take a look at the size of our samples. Since the sample size is 100 and 100 is bigger than 30, the central limit theorem applies. Therefore, I'm now allowed to use these properties of sampling distributions in their connection to the population. The mean of the sample means is supposed to be the same as the population mean. which was 6.8 hours. So again, this is now called the mean or the average of the sample means. So picture taking a sample of 100 sleep times, adding up those 100 sleep times, and dividing by 100, and writing that down, and then repeating with more samples. We're saying that the average sleep time will be 6.8 hours. To calculate the standard deviation of the sample means, we use the property that it's the population standard deviation divided by the square root of the size of the samples we're taking. We're told that the standard deviation is 1.4 hours, and we're dividing that by square root of our sample size, which is 100. And if you divide that out, you're going to get a sample standard deviation of 0.14 hours. That's the standard deviation of the sample means. So remember, that's an indication of how spread out the data is from the mean. And this is a pretty small number, so it sounds like they're not very far spread out from the mean. In part B, we're asked to sketch a graph of the sampling distribution. The central limit theorem tells us that the sample distribution is going to be a normal distribution as long as we meet that condition of having a large enough sample size or drawing from a population that's normally distributed. So I'm going to be sketching a normal curve, and to do that, I need a number line. And on this number line, I need to fit a mean of 6.8 hours and a standard deviation of 0.14 hours. So the mean is roughly 7. So I'm going to put 7 in the middle of my number line. I'm going to count off to the right and to the left. My mean is 6.8 hours, so that's where the middle is going to be. So I'm going to put a little dashed line at approximately 6.8. That should be the line of symmetry for the normal distribution that I draw. And again, we said we have a very small standard deviation. The standard deviation of 0.14 means the normal curve is going to curve from this peak, curve downwards until we get to 0.14. And then remember, at that first standard deviation, it changes and curves upward. So you're going to see that we're going to have a very narrow normal curve in this example because that standard deviation is so small. So we're getting a big peak in the center and very little spread on our normal distribution. Here's another example. Assume the training, and this is heart rates, of all 20-year-old athletes are normally distributed with a mean of 135 beats per minute and a standard deviation of 18 beats per minute, as shown. Random samples of size 4 are drawn from this population, and the mean of each sample is determined. Find the mean and standard deviation of the sampling distribution of sample means. Okay, again, having to list all the samples of size 4 could take quite a while in calculating all of their means. So what we hope is that we can apply the central limit theorem. Now, in this case, our sample size is 4, and 4 is well below 30. So the first condition of the central limit theorem doesn't apply. However, notice that it says we are to assume that the heart rates of all of the 20-year-old athletes are normally distributed. Since our data comes from a population that is normally distributed, the central limit theorem does apply here as well. So for part A, to find the mean and standard deviation of the sampling distribution of sample means, we know the mean for the sample means will be the same as the mean for the population, which we were told is 135 beats per minute, which I will abbreviate BPM. And the standard deviation of the sample means is the population standard deviation divided by the square root of the sample size. Standard deviation for population was 18 divided by the square root of 4, which is really just 18 divided by 2, which is 9 beats per minute. Now we're supposed to sketch the graph of this sampling distribution. Again, we know it's going to be a normal distribution with the center of the distribution being at 135 beats per minute. So I'm going to go ahead and set up a number line where 135 is roughly in the center. Because my standard deviation is 9 this time, I'm not just going to count 1 unit in each direction. I'm going to round 9 off to 10, and you'll notice I went and counted off steps of 10 in each direction from 135. So the line of symmetry for this distribution needs to be at the mean, which is 135. And if my standard deviation is 9 beats per minute, again, my curve is going to curve downward until I get to 9 units away, and then it's going to start to curve upward. And what you should notice is we should have a wider, more spread out distribution this time because our standard deviation is fairly large. So we're not going to have as tall a peak because the data is not as close to the mean as the previous example. We'll have a shorter peak with more of the data more spread out. The last part of this section makes that important connection between probabilities and the central limit theorem. So now that we know the central limit theorem connects a sampling distribution to a normal distribution, we can use the skills we learned for finding probabilities of a normal distribution, namely using things like the standard normal table to calculate probabilities. We can find the probability that a sample mean will lie in a given interval of the mean sampling distribution. To transform that mean to a z-score, which again, the z-score is how we find the position in the normal curve, we're going to do the same thing we did before, the value minus the mean. And you're used to seeing it say here divided by the standard deviation. We're going to divide by the standard deviation for the sample means, which is also known as the standard error. So here's that z-score formula written out. This was in words, this is in symbols. And remember that the mean of the sampling means is going to be the same as the population, so you can see we've made that substitution. And the standard deviation of the sample means has been replaced by its equivalent formula as well. So primarily, you're going to be using this formula to begin to locate probabilities. Example 4 says, suppose the average number of miles driven each day by 16 to 19-year-olds is 20.7 miles. You randomly select 50 drivers ages 16 to 19. What's the probability that the mean distance traveled each day is going to be between 19.4 and 22.5 miles? So we're taking 50 drivers, we're recording how far they travel in a day, we're finding that average. And what is the likelihood that that average for the sample will be between 19.4 and 22.5? We're asked to assume that the standard deviation of the population is 6.5 miles. So step 1 is, again, you have to verify that the central limit theorem is going to hold. So notice we're selecting 50 drivers, and a sample size of 50 is bigger than the necessary 30, so therefore central limit theorem applies. I find the mean and the standard deviation of the sample means first. So the mean is the same as the population mean, which was 20.7. And then the standard deviation of the sample means is the population standard deviation divided by the square root of the sample size, which gets us 6.5 over the square root of 50. And in this case, I'm not going to go straight to getting a decimal here because we don't want to round. This is going to be a messy decimal. We want to preserve the accuracy. So what I'm being asked to find is the probability that the sample mean falls between these two numbers. The next step is going to be to get the z-scores for each of these numbers. So to do that, this is where I'm now going to bring in this new formula that says the z-score, if I'm calculating for 19.4, is going to be the sample mean, which is that 19.4, minus the population mean, which we were given, 20.7. And we're going to divide that by this fraction, which is exactly the fraction we just set up. So we're dividing by 6.5 over the square root of 50. Now, when you're putting that into a calculator, you've got to be very careful here and make sure you keep this entire denominator in its own set of parentheses. You should go ahead and pick up a calculator and make sure that you're able to type this in. And when you do, you should get approximately negative 1.41. We're going to take 2 decimal places here because our data was given to 1. I'm going to repeat the process to find the equivalent z-score for 22.5. And for 22.5, you should get 1.96. So calculating the probability that the sample mean falls between these two values is the same as calculating the probability of the z-scores falling between negative 1.41 and 1.96. You'll remember that the standard normal table always gives the probability of being less than a certain z-score. If you want the probability between two z-scores, you're going to subtract their probabilities. So in other words, I'm going to find the probability of being a z-score less than 1.96. I'm going with the bigger one first because that's going to have the higher probability, minus the probability of my z-score being less than negative 1.41. And again, I'm using less than symbols here because that's what the standard normal table uses. Here, once again, is the standard normal table where we look up z-scores to find the probability of a value being less than that z-score. The first one I'm supposed to look up is 1.96. So I go to the row 1.9, I read across to the heading 0.06, and the first probability is 0.9750. Then to look up the second z-score of negative 1.41, I'm going to switch tables to the one that shows the negative z-scores, go to negative 1.4, and then go to the column labeled 0.01, which gives me the number 0.0793. I'm going to fill in those probabilities, subtract them, and that gives me a final answer of 0.8957. And remember to convert that into a percent. You can just move that decimal place over 2 places. So we get roughly 90%. So what does that actually mean in terms of this situation? This means of all the samples of 50 drivers, about 90% of them will drive an average each day between 19.4 and 22.5 miles. So you can see how the central limit theorem is super important because it lets us use a tool that we already have to calculate probabilities. One last example is example 5. The mean room and board expense per year at four-year colleges is $10,453. You randomly select 9 four-year colleges. What's the probability that the mean room and board is less than 10,750? Assume that the room and board expenses are normally distributed with a standard deviation of 1,650. So once again, we must make sure that the central limit theorem applies. So we are only selecting groups of 9 four-year colleges, and 9 is less than 30. So we don't fit the first condition of the central limit theorem. However, we are told that we can assume that the population is normally distributed. So because of that, we are allowed to use the central limit theorem. So the first thing, again, you're going to want to do is calculate the mean and the standard deviation for the sample means. We use the population mean, which was $10,453. And to find the standard deviation, we take the standard deviation of the population divided by the square root of the sample size, which gives us 1650 divided by square root of 9. And this time, this is a nice value because square root of 9 is just 3. We can do 1650 divided by 3 and get exactly 550. So in this case, it is okay if you go that one step further and get a number because we're not cutting off any decimal places. It's an exact value. Next, we determine which probability we're looking for. We want the probability that the mean is less than 10,750. In symbols, we want the probability that the sample mean, x bar, is less than 10,750. We're going to begin by getting the z-score for 10,750. And again, I'm using that same formula from up above. You're going to take that sample mean minus the population mean, and you're supposed to divide it by the standard deviation of the sample means, and we don't need to use this fraction. We can use what it's equivalent to because it's an exact value. If you type that in, you're going to get a z-score of 0.54. We're going to take 2 decimal places to use our standard normal table. The probability we're looking for is equivalent to the probability of a z-score being less than 0.54. The probability of z-scores being less than some number is exactly what you get when you read the standard normal table. You're going to look up the z-score of 0.54, and whatever probability is in that part of the table, that is your answer. And it turns out that's 0.7054. Again, that's roughly 71%. So to put that in words and explain what that means, we would say about 71% of the samples of 9 four-year colleges will have a mean less than $10,750. So make sure that when you're calculating the probabilities based on the sample distribution, you have the standard normal table handy.